Hello everyone. Let's talk about section 1.2, which is measuring and constructing segments. Now in this section we are going to be talking a lot about segments, but we're not going to spend very much time measuring them with like a ruler or constructing them with a ruler either. So we're going to be doing some other kind of geometric things with our segments today. So when you're talking about measuring something, whether you're using a ruler or not, well, the major thing that we're interested in is the distance. And so right here what we have is the distance, and we have a very basic definition. The distance is the difference in the location of 2 points. Now when I use the word difference, I'm thinking about it in kind of a mathematical way, so I am using the idea of subtraction. Okay, so in this kind of situation, what you want to do is you're going to look at for this difference by taking a look at some locations, and you're going to want to find the bigger location, which I'm going to call the max, and then what you would want to do is you would want to subtract the smaller location, otherwise what I'm going to call the minimum, and when you do that subtraction, you are going to get your distance. This is going to work all the time, and it works really nicely. Now, you might be thinking to yourself, I have an actual formula, Mr. Slomka, that I know about for distance, and it works really, really well. And you probably do. You used it last year in Algebra 1 class, and it was really fantastic. And I don't want to take that away from you. I'm not going to make you backpedal or anything like that. If you remember your distance formula, that is fantastic. But we are in a geometry class, so we're not necessarily going to be always working with the exact same tools that we learned about in an algebra class. So if you remember your distance formula, that's great. You can definitely use it as much as you like, but you might not need to use it as much as you might think. Next, let's talk about two very critical pieces that we're going to discuss today. One is congruent segments. This is a huge deal. And last time we were talking in section 1.1, we had spent some time talking about notation, and that is really a big deal here. So when you are talking about two different segments, these segments can be considered congruent if they have the same length. So these are two unique and individual segments, but as long as they're the same length, that means that they're going to be called congruent. Now you're going to mark this in a couple of ways. So here's your first one. So if you do have these segments and they're the same length, then what you can do is you can come through and you can put a tick mark. Or if you'd like, you can put 2 tick marks, or you can put 3 tick marks. Anytime that they have the matching number of tick marks, it's going to let someone, including yourself, know that they are equivalent in length. Okay, so now let's talk about how to write that down using some notation. So when we are talking about the distance from point A to point B, what we're going to do is we're going to call it AB. And when we're talking about the distance from C to D, we're going to call it C to D. So these two pieces right here have everything to do with distance, which is what we were just talking about earlier. And we are stating that the distances are equivalent. So this one right here is talking about distances, and our distances are equivalent. Now, if you want to talk about the segments, you're going to need to include some more notation. So we've included these lines over the top of the segments. Now, the segments cannot be equal. The reason why is because if two segments were equal, it would actually just be the same segment. It would be right in the same location, right on top of itself, and that would be how a segment is equivalent. That's impossible. These two segments live in two different places. They are very similar to one another because they have the same length, and they're even pointed in the same kinds of directions, but they can't be equivalent segments. So what we do instead is we talk about segments being congruent to each other. So this little symbol right here is dealing with some segments, and this guy right here is our symbol for congruent. There you go. Congruent right there. Okay, so now, this is a very big deal here for me and for geometry teachers in general. I need you to make sure that you notice that there are going to be no segment lines here, and there's no congruent squiggle over the top. When you are using these segment lines, then you will use your congruency squiggle that's going to go right over the top right here. So these are very similar to one another. One has to do with the distances, one has to do with the segments, one has to use equivalency, and one has to use congruence. So they are very, very similar, but I want you to make sure that you can tell the difference between them. Let's put it to work. So right here, what we have is we're going to be talking about PQ and RS. Now we are going to construct PQ. The notation tells me that what they want is a segment, not a line or a ray. So what I'm going to do is I'm going to start at point P, and I'm going to cruise over to point Q, and when I hit point Q, I'm going to stop. I won't be extending any further than that. Same thing for RS. It is another segment. So I'm going to start here at R, and I'm going to mark my way down to S, and then when I hit S, I'm going to stop. Okay, so now if you want to know if one segment is congruent to another segment, then that means you also need to know if their distances are equivalent. So that means we're going to be paying close attention to the distance of our two different segments. So let's see if we can figure out what those two distances are, and then once we have figured that out, then we can make our choice. Okay, so let's start with PQ. So PQ right here is going to start over here in the second quadrant, and then it's going to head over towards this first quadrant. Now remember when we were talking about our distance formula up here at the top, I had mentioned that the simplistic distance formula was max minus min, and I had also mentioned that you could use your more complicated distance formula. Now in either of those cases, you're going to need to know what the locations are for the points P and Q. So I'm going to find that. P is 4 units over, which is going to be negative 4 because it's to the left, and it's 3 units up, positive 3. Now Q over here, that's 3 units to the right, positive 3, and 3 units up, another positive 3. Now I want you to notice that this is a horizontal line. So what you'll find a lot of times with these basic horizontal lines and vertical lines, which is what I'm going to start off giving you, you'll notice that there is a repeated value, these guys right here. The height of both of these points is identical. So that means that it's also not very valuable when we're trying to find out what the distance is. You can focus on just the x values right here. And once again, our technique is to take the maximum one, 3, and subtract from it the minimum one, negative 4. When you do that, you will get the full distance. And the full distance in this case is now going to be 7. Now let's do RS. RS is a vertical line, so you can do it in very much the same way. You can find out the location of R, which would be negative 1, 4, and S, which would be negative 1, negative 2. Now once again, they have a repeated digit. This is a vertical line, so the x values are going to be the same, and so you can do the same kind of max and min work. That would be 4, take away a negative 2. Another technique that works really well that you probably already thought about before I'm even mentioning it is you can do some bunny hopping. So if you want to bunny hop your way, you can do that. So you can bunny hop from up here. You can go 1, 2, 3, 4, 5, 6. And if you like bunny hops like I like bunny hops, that's a fast and efficient way to work on it. I don't see too many people miscount their bunny hops, and so it's a good way to go. So now the last question is it true that the distance from P to Q is the same as the distance from R to S? And the answer to that question is no. No, these are not the same. That means that these guys right here, the distances are not equivalent to each other, and that means that our two segments right here are not going to be congruent. To state something is not congruent, you're just going to put the slash through it. So then determine if PQ is congruent to RS, and that is going to be not the case. PQ is not congruent to RS. It's not true. Okay, so now we've talked about our first critical piece, which is our congruent segments, and I talked to you about the notations, which is one of the most important things. Here is our second most important piece of the day. So our second most important piece of the day is the segment addition postulate. This is a very simple concept right here, but it really shows up 100 million times. So if you can get it nailed down and you can use it backwards and forwards and upwards and downwards, you're going to be in great shape. So this is a basic idea about a small segment. And so what we're talking about right here is we would be talking about a segment like AC. Now in this segment AC, what you're going to have is you're going to have a third point, which in this case is B right here, and that's going to be between A and C. Now, if you notice, it's not exactly perfectly in the middle between A and C, but rather it might be off to one side. It could be perfectly in the middle, but most likely not the case. And what you're going to do is you're going to be able to think about AC by breaking it up into two smaller pieces. AC is the big distance right here, but you can break that up into two smaller pieces, which would be AB and then BC. And the way that this is all going to work out is if you take those two smaller pieces, AB plus BC, it will be equivalent to AC. Now, if you look at all of these, you're going to notice that I'm talking about distances. There are no segment notations over the top of these, so all of these are referring to the distance. The distance from A to B plus the distance from B to C is equal to the total distance from A to C. What I like to do is I'm a little more basic than that. And what I like to do is I like to say this right here, A to B, that's a short distance or it's a little distance. B to C is another short distance or another little distance. And from A to C, that's the big distance. So what I like to think about in order to keep this as simple as possible for me is I like to think about little plus little equals big. Super. Okay, let's see if we can take this and put it to work. So now what I have for you right here is I've got a little example problem that I'd like you to try out. So I am going to be finding the distance from D to F. So now D to F is going to be this segment right here. And what I notice is that there's a point in between D and F, which is going to be point E. And so for point E right here, that's going to split up my total distance. But that's okay. I can take this short distance, or this little distance, 23, and I can take this short distance, or this little distance, 35. And if I take my 23 and my 35 and I add them together, that will give me the full distance that I want, which is going to be 58. Now GH is a little trickier. For GH, what you'll notice is that GH actually is one of the little distances. I already know what the full distance is. It's actually 36. My other little distance is a 21. So here's what I'm going to do. I'm going to set this up. You might have a shortcut that you're already thinking about, and if you do, that's great. Go with your gut. But if not, you can follow my technique, and it'll work out very nice. I'm going to use the technique that is going to go as closely as possible to what I've already stated, and so this is what I'm going to do right here. I'm going to say that if you start off with your first little distance, which is 21, and you add to it your second little distance, which I do not know, so I'm just going to call it by its name, GH, then that would be equivalent to the big distance, which is 36. So what I've done is I've just taken my pieces and put them where they belong. Now, after that, now I need to solve this. Algebra is still important, so we're going to use our algebra skills here. We're going to move this 21 over to the other side by subtracting it. And that is going to leave the GH alone. And 36 minus 21 is going to take us down to 15. The distance from G to H is 15. Okay, now I have another example problem that is very, very similar to that right here. And I'd like you to try to answer that for me. I also have another example problem right here about the state of California. This one is a story problem, and I'd like you to see if you can answer that one as well. Once you've answered these two questions, that means you're prepped and ready to go. It's time to move on to the in-class activity and your homework.